Hi everyone, I'm Rohit Kumar Singh, teaching assistant for the course Experimental Physics 2. So this is our fifth live session, and today we will discuss some concepts of related to prism, and uh, I will try to recap all the relevant formulas, and then we'll solve some sample problems. Okay, so let's start. So, yeah, what is a prism? So, you all must have seen a prism in your life, right? So, you know that if uh, you you shine a light on a prism, white light, it will get dispersed into all the seven colors of the rainbow, right? So, that's the main property of prism. But for now, suppose we have we have a light source which only emits a single color lights. Suppose this is red, okay? So now how its path will be like inside the prism. So first of all, let me put some uh, okay, so labels here. So suppose this is A, B, C, 3. Uh, so actually the prism. So this is a two-dimensional view of a prism. Okay. In reality, the prism will look something like. So let me try to draw it. Uh, so suppose I'm bad at drawing, but I'll try. Something like this. Okay. So and I'm drawing this side only. Okay. So this angle is angle A, okay, and then we have B and C. So A is there, B and C is there, okay. So this is a two-dimensional diagram of a three-dimensional object, and these two sides, this side and this side, are this AC and AB here, okay. Uh, so you have to imagine, you must have seen a prism, right? So that we can think about it. Okay, so now you know that so in the outside we have air, and inside the prism is made up of some glass material, and it will have a refractive index which is greater than air. So what will happen? So suppose this is the normal on this AB surface. So when the light passes through a rarer to denser medium, what happens? Can anyone say? Will it bend towards the normal or away from normal, or will it continue in the same path? What do you think? What will happen? You are free to answer here. What happened? Towards normal. Okay. Yeah, because it is a denser medium, and we have the Snell's law, right? Sin I by sin R. The ratio is equal to the relative refractive index. So since this refracting index of glass is larger than the air, the refractive angle will be less, right? This is R and this is I. So, and then, uh, okay, maybe I have bent, bended it too much. So this is the normal. It will bend like this, okay? This is R angle, this is the I angle. Then it will continue like this. Now what will happen? So we have this normal. Now what will happen? Let's write it R1 away, because here you have again air and the light is going from a rarer to denser to rarer medium. So here what will happen is this. So this will be, now this will be the incident angle, but let's denote it as R2, and it will the incident the refractive angle, let's call it E, like this. E here is the emergent angle because it is emerging from the prism, that's why it's called the emergent angle. So now you see this path of light which was coming inside, now it is going through this path. So it has deviated its path, and the deviation which is happening here, you can calculate it. So we can extrapolate it like this, and this final path, and this angle is what we call the angle of deviation. Okay. So yeah, just remember these terms, and this angle of deviation you can actually calculate in terms of refractive index of prism and this angle of the prism. The A is called the angle of the prism. Okay? And so I'm not doing the derivation here. I think it's been done in the lectures, but if you have any doubts, you can ask me in the derivation. Okay. So I'll write out the formula for deviation delta, and it is this mu minus 1 into A. So this mu is the refractive index of the prism and A is the angle of the prism. And here is one condition. Okay, the condition is the prism should be a thin prism. Okay, this formula is only valid for a thin prism. That means the angle A should not be much greater. I mean, it it should be of the order of uh, 10 maybe most. Okay, otherwise this formula will not work properly. Because in the derivation you might have seen that uh, uh, there are some approximations like sin I has been taken as I, right, and sin R1 has been taken as R1, and uh, this is only possible for a thin prism. Okay, so yeah, this is one uh, precaution before using this formula. And no, this deviation, you can vary the you can vary this angle of the prism and the refractive index of the material, and this deviation will change, right? If the prism is so starting from a thin prism, you can vary the thickness of the prism, and so there is a formula. uh, so there will be a point where this deviation will be minimum. Okay, so you will get a curve like this. So suppose this is the, on x-axis I'll keep angle of incidence, which is I, and here you have angle of deviation, angle of deviation. Okay, so when the angle of, so if you vary the angle of incidence from I to, suppose E is here, okay, somewhere, so you will get a curve like this. Okay, and here where I is equal to E, that means this angle, the angle of incidence and angle of emergence, where these both are equal, there will be a minimum deviation. Okay, so this is a beautiful symmetry that we have here. So suppose this prism is here, and this is the angle of incidence I, and if the angle of emergence is same as I, okay, I equal to E, the light ray will be just parallel to the base of the prism, and this deviation that you are getting will be minimum. Okay, you can derive this formula, you can derive the formula for uh, angle of minimum deviation, and so let me write it. It's called the prism formula. uh, it is given as this. You must have seen this formula and used it also. Sine a by 2. Okay, so this delta m here is the angle of minimum deviation, and this only happens when I equal to E. Okay, so then yeah, then comes the part where uh, we have the deviation, we have the dispersion of the prism, dispersion of the light by the prism. Okay, so let me erase some of the things. Okay, so as I told you, prism can also uh, disperse the light. So if you shine a white light, suppose the sunlight, it will be dispersed into all the 7 colors of the rainbow, right? And the dispersion is so the dispersion is caused because for each wavelength of light, the mu, that is the refractive index of the prism, is different. Okay, so each let me show you. So this is a white light which is made up of all the 7 colors of the rainbow. Okay, and uh, what happens is that it consists of all the 7 colors, and the refractive index of this prism for all the 7 colors. So suppose mu r, there are violet, and then there is yellow. They are all are different. Okay, so this bending of the light, this deviation of the path which is happening, since it depends on the mu here, as you have seen, so it will be different for each color of the light. Okay, and that's why when they will come out, what will happen is they will be separate. So you see the rainbow. Okay, maybe I can show it by different colors. I should have drawn by different, draw for the sake of aesthetics. Okay, so let me take red. Oh, shit. Everything turned to red. Okay, leave it. I don't know how it works. So you understand, right? How it happens. So since these all the refractive index are different, the deviation will be different for uh, all the colors, and when they will come out, they will be separated. And so the dispersive power of a prism is given as delta of violet minus delta of red, and the mean deviation. Okay, and the mean so this is the deviation power of a prism. So how much it can deviate a violet ray in respect to the red ray. Okay, red light. So this is defined as the dispersive power. So this formula will also be used in a problem. You will doing the problem, you will understand more how can we use it. Okay. Okay, then that's all, I think. If you have any question here, you can ask. Then, if not, I'll move to our problem solving session. I just did a quick recap of the concepts, some concepts and some formulas. Okay, is it fine? Anyone have any doubt? Okay, thank you. If everyone is fine, then let me go to our first problem. So can you are you able to read the question properly? The font, okay? So okay, okay, thank you. So the question is, a diver at a depth of 5 meter in water, uh, so the refractive index of water is given, it's 4/3, sees the sky in a cone of semi-vertical angle, uh, figure given below. Okay, so there is a diver here, and this is all water. Okay, and you have to find the semi-vertical angle, this angle. Okay, through which through the circle of which he sees the sky. So this type of problem I also solved in our last live session. So like there was a problem that there is a source of light here at the bottom of a bucket, and it is emitting light in all directions. So what is the surface area of the circle through which the light emits? So the same problem is here, just here, instead of light source we have a diver, and this is uh, yeah, I think this is the ocean or something instead of bucket. But yeah, same concept is there. uh, so if you guys were not there, or maybe let me go through the solution once again. It's a very simple problem. I mean, it looks complicated. So anyone has any idea uh, how to deal this problem? Anyone? Let me give you a hint. You can use the concept of you can use Snell's law here, because suppose we have water here, and here we have air, and so light is passing from water to air. So something will happen, right? So that you can use to calculate the this angle, this semi-vertical angle of the diagram. That his field uh, point of view. If anyone, if no one has any suggestion, let me solve it. So suppose this is the s- so this is this cone that that will be made. So do you understand how a cone like shape is being made here? So the diver is here. So this is the depth, 5 meter, and he sees that he can only see through see the sky through a cone, and this cone will have some radius r. Okay, and so that means that the light light after this line, they are getting totally internally reflected. Okay, this light is not going out, or you can think of it this way, that the light from above uh, is not coming inside. Okay, uh, let me draw a better picture. Okay, so this is the normal. This is the water air interface. Okay, here is water, here is air, here is water, and this is the normal. Okay, and so what I'm saying is, after this, uh, all the light is getting totally internally reflected. That's why he's not able to see the sky above after this. Okay, so uh, which incident angle uh, there should there be, that after this all the light should go out? So you know there is a critical angle uh, after which all the light after which all the light gets totally internally reflected, right? So this cone is made up of all the rays of the light which are getting uh, refracted through a critical angle, through 90 degree, that is the incidence angle is critical angle. Okay, so that means is this ray of light is going at 90 degree here. Okay, and this angle is your critical angle theta c. So since these two normals are parallel, this will also be the theta c. Okay, and you can use the Snell's law, which is sine I, that is theta c, by sine r, which is 90 degree, is equal to mu, refractive index of water. And so you will get theta c as sine inverse of, so sine 90 degree is just 1, sine inverse of mu. So this is just sine inverse of 4 by 3. Okay, so this is your correct answer. So any question? I mean, this question looks complicated, but if you think about it, it's very simple. It's just the concept of total internal reflection. Because light is going from a denser medium to rarer medium, there is a limit up to which you can see. After that, all the lights will get totally internally reflected, right? That will happen in all the directions. So that's why you have a cone like this. So if you have any doubt, you can ask. Is it fine? Okay. Okay, then let's move to the next problem. So here the question is, a prism having refractive index 1.414. Okay, so mu is given 1.414, and the refracting angle R 130 degree. Okay, so has one of the refracting surface silvered. So as I mentioned, in the prism we have two surfaces, this AB and AC, and one of them is silvered. So suppose this one is silvered. Silvered means it will reflect all the lights that will incident on it. Okay, so a beam of light is incident on the other refracting surface. So suppose this is the beam of light coming. Okay, and it's saying that it will retrace its path if the angle of incidence is. So at what angle of incidence will it retrace its path? That means, sorry. So that means it will obviously bend towards the normal, and then it will go and come back to the same path. So at what angle should this be happening? Anyone has any idea? When it will happen? And this Yeah, this is 30 this is 30 degree. You understand the question now? This beam of light, it should retrace its path uh, at which angle of incidence. This angle we have to find. It's I. Sorry. So how do we calculate it? So it's also an easy problem. So the only thing is this retrace of path is only happen if this uh, beam of light after bending falls on this surface perpendicularly, right? Because let's say uh, if it falls like this, that like I'm showing, it will be reflected like this, right? If it falls like this, it will reflect like this. Only when it falls on it perpendicularly, it will reflect back, because the mirror reflects uh, light perpendicularly, which is normal to it. Otherwise, if any angle is there, it will reflect it like this, right? So that's why this got messy. So let me redraw it. So this is silver, beam of light is coming. This is the normal here, and okay. So this is not looking like normal. So let me draw it. Okay. So if this light is normal, only then it will be reflected back and retrace its path. Now we have been given this angle, which is 30 degree, and you know that this angle is 90 degree. So this angle will be 60 degree, right? And this is 90 degree, so then this will be 30 degree. Sorry. Okay, just the properties of a triangle. And so you can calculate this angle I using the Snell's law. So Snell's law, what does it say? Sin I by sin R is equal to mu. So mu is mu is 1.414. Okay, so sin I is equal to 1.414 into sine of 30 degree, which is 1 by 2. Okay, and if you okay, so sine I will be half of 1.414, but it would be 0.707, right? Oh, sorry. Mm, yeah, that is correct. And this will give you I equal to 45 degree. You can calculate it on a calculator. Okay, so for the incident angle, 45 degree, you will have the path of the light ray retraced. Okay, so this was also a simple problem. Is everyone fine with it? Any doubts? Just I've used the Snell's law, and this common like using the common sense, like the retrace will only happen if it falls perpendicularly on this silvered surface. These two concepts were only needed. Okay, so let me write it. Retrace will only happen if light falls on silvered surface perpendicular. Okay, so if no one has any doubt here, let me move to the next problem. Uh, Here we have a prism of a certain angle, and it deviates the red and violet rays by 8 degree and 16 degree respectively. So like I told you, prism deviate different colors by different angles. Okay, so suppose this is the red color light. uh, okay. Why am I not able to draw separately? Okay, this is red, and so and this is suppose the violet. They are coming, they will deviate by different angle somewhere. Okay, uh, like this, suppose, and another prism of same angle deviate the red and violet rays by 12 and 18 degrees. So there is another prism. Okay, another prism means this angle will be different. So this is A2, this is A1. Okay, and uh, this deviate the red and violet colors by different angles. Now the prism are small angled, that means we can use that formula of deviation, which is mu minus 1 A. Okay, this formula can be used here because the angle is small, so they are thin prism, and they are made up of different materials. So this is made up of some different material, and this is different. So the refractive index will be different, mu1 and mu2. And the dispersive powers of the materials of the prism are in the ratio. So we have to calculate the dispersive power W1 by W2. Now, what is the formula for dispersive power? So it is the mu for red minus mu for violet divided by mu mean. Oh no, sorry, not in terms of refractive index. Let's write first in terms of deviation. Delta of red minus delta of V is by delta mean. Okay, delta is the deviation. So this is the dispersive power, and we know that from this formula we can write it in terms of refractive index. Okay, so but we have been given here the deviation angle of red and violet. So let's first calculate for this prism. So what is the delta R? So for red it's 8 degrees, and for violet it's 16 degrees. Okay. Uh, oh wait, I think the formula has delta V minus, because always the deviation angle for violet is more than the red. So this is like this. Then we have 16 minus 8, and the mean deviation is just the mean of 8 and 16. So what is the mean of 8 and 16? So 8 plus 16 by 2, so it is 12. So divided by 12, and this will be 2 by 3. Similarly, for second prism, we have delta V and delta R as 18 degree and 12 degree. So let's put that here, and the mean of 18 and 12 is 15, because 18 plus 12 is 30, and divided by 2 is 15. So this comes as 2 by 5, and the ratio W1 by W2 is what? So you just divide these two. 2 by 3 by 2 by 5, 2 get cancelled, 5 by 3. So W1 ratio W2 is just 5 by 5:3. So this was a simple application of these two formulas. Okay. Yeah. Anyone want to say anything? Okay, if it's fine, then let's go to the next problem. So this you might have heard of Nicole prism. If not, I'll explain a little bit about it. So the question here is, the working of Nicole prism is based on the phenomenon of. So there are four options: refraction, reflection, diffraction, and double refraction. And this double refraction is also called birefringence. Okay, so uh, can anyone tell me what Nicole prism is and what it does? If anyone has any idea. Hello, are you able to hear me? Yeah, someone raised his hand. Yeah, Satyanarayan, you want to say anything? You can unmute yourself and speak. Atharv Singh, do you know what Nicole prism is? Okay, okay, no problem. Okay. Yeah, yeah. Double refraction. Okay. So how does it happen? What is double refraction? Can you explain? uh-huh, okay, uh-huh, uh-huh, mhm. Yeah, 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 yeah. Yeah, that's true. So, a nickel prism is made up of a specific material, calcite or something. I don't remember. So it has of a shape like a rhombohedral. To draw it properly, okay. Maybe like this, and it has two different material. Okay, so this one and this one, they are two different material, and so and there is a interface here diagonally. Okay, so now a light ray is entering this prism, and this is suppose ordinary light, I mean a simple unpolarized light that you see, and you know that a light wave, a light ray is made up of electromagnetic waves. So there are electric fields, and you might have studied that electromagnetic wave is has a form of a sine function. So it it five so basically the electric and magnetic fields, they vibrate perpendicular to each other, and that's what we call a light ray propagation. Okay, and so this vibration of electric field determines the direction of polarization. So an unpolarized light has direction of polarization in all the direction. Okay, so we can take different two different polarization perpendicular to each other. So suppose I'll denote the one which is polarized with the plane of this screen. Okay, and I'll denote it like this, and one which is perpendicular to the screen, like which is coming out and going inside, like a dot. Okay, so you can represent a light ray like this. So it has both the components. Okay, it has it has both ordinary and extraordinary, that you call two components of polarization. And when it enters this crystal uh, like this, uh, when it when it's incident on this interface, what happens is that one of the component will be totally internally reflected, and one will pass through like this. Okay, so this component of light will be reflected, and this component will only get passed. So you can get a polarized light through this process. So this material is used in, so suppose you might have used this Polaroid specs to like cut out the light coming from the sun. So these objects use the concept of birefringence or double refraction to remove some of the light. So it reduces the intensity of the light by half. Okay. Yeah. So this is the Nicole prism, and it works on the principle of, yeah, 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 yeah. Tell me. Mm-hmm. Uh-huh. Uh, no, sorry. So the calcite crystal and the interface. What about the interface? I mean, I have forgot the material which is it is made up of. I know the calcite is used. Yeah, yeah. That material. Can you write it out? I am not able to hear you properly. Can you write the? No. Yeah. These two are both calcite, I think. Yeah, you're right. These two are calcite, and this interface will be of a different kind of material because the light is incident here, na? Yeah, Canada balsam. Okay, yeah. Now, yeah, you're right. So this will be calcite, and this interface is made up of Canada balsam. Yeah. Now I remember. Okay. Yeah, but the concept that I have discussed is true. So one of the light will be totally internally reflected, and one will pass through one of the component. So that's how you get a polarized light using a Nicol prism. So Nicol prism's main use is getting a polarized, and you can also analyze if the light coming to you is polarized by putting another Nicol prism here. So you can put another Nicol prism here, and if the light passes through again, you will know that it has been polarized in this direction. And uh, if it doesn't, like, and if it bends here, so you will know that it is not polarized. So like that, you can use the Nicol prism. Okay. So yeah, thank you, Satyanarayan, for correcting me. Okay, then next problem we have here is identify the factor on which the angle of deviation of prism does not depend. So, can any one of you answer this? This is a simple problem. So, option is angle of incidence, the material of prism, area of refracting surface, the wavelength of light used. So, uh, can you guys answer this one? The deviation that is caused by the prism. So you have this prism, light ray will come, will go like this. This is the deviation angle. Okay. So at on which parameters does this uh, delta depends on? It doesn't depend actually. So out of these, which does not matter for this angle of this deviation? Please answer. You should be able to answer this, I think. Okay, so let me go one by one. So does it depend on yeah, anyone is why do you think so? Why not? Why do you think so? Why not the angle of incidence? So we have this formula of deviation, right? Mu minus 1a. Here you don't have the angle of incidence in this formula, right? Only this angle of the prism is there and the this refractive index is there, right? So I mean, if you look at this formula, it should not depend on the angle of incidence. Okay, then we have material of the prism. Yeah, material obviously. This refractive index, uh, it is because it is different for different types of material. So obviously B is not true. Then the area of refracting surface. So here also we don't have area of refracting surface in this formula. So uh, I don't know what. Uh, let let me leave it. And the wavelength of light used. So as I told you, the wavelength of so the deviation for different wavelength of light is different. So obviously this is also not true because the refractive index of a material depends on the wavelength of light. Okay. So now we have A and C. So yeah, let me remind you. I I showed you one plot like this, right? Here we had a angle of incidence, and this y-axis we had delta, and when I change the angle of incidence, this deviation changed, right? And it was minimum when the angle of incidence and angle of emergence was equal, correct? So yeah, this way this delta depends on the angle of incidence. Okay? Uh, and so this one is also not true. So the correct option is C. The area of refracting surface does not make any, I mean, does not impact the angle of deviation in any way. Okay. So yeah, and also because this formula in this derivation of this formula, this angle of incidence has been used in many steps. So if you go through the derivation of this formula, you will see how angle of incidence uh, can change the delta. Okay, through the derivation. So anyone has any question here? Okay, if not, then next problem. So here the question is calculate the refractive index of the material of an equilateral prism for which the angle of minimum deviation is 60 degree. Okay. So we have a equilateral prism. What does it mean of by equilateral? So equilateral triangle, you know, which all angles are equal. So here also this surface that I am drawing of the prism here all the sides, all the angles will be same. Okay, and here the question, here we have given the angle of minimum deviation, which is 60 degree, and we are asked what will be the what is the refractive index of the material. Okay, so I mean, this is also very simple application based formula. You know the prism formula, right? Which is given like this. So mu is sine delta n plus a by 2 by sine a by 2, right? So we have delta m given here, uh, and we want to find mu, the refractive index, but we don't have a. So what will be the a here? A 60, yeah, simple, right? Because it's a equilateral triangle, all the angles are 60 degree. So just put everything. Sine 60 by plus 60, 120 by 260 degree divided by sine 60 by 2 sine 30 degree. It will be under root 3. Yes, under root 3 by 2, that will get cancelled. So this is the correct answer. Refractive index will be under root 3. Okay, this was a very simple problem. Okay, the next problem. What is the angle between the incident ray and the emergent ray in a prism called? Angle of deviation, obviously. I should have put this question in the first place. Okay, this was a simple problem. It has nothing to do with anything. Okay, so now we have a good problem here. So the question is, calculate the dispersive power of a prism made up of crown glass where mu v and mu r is given. So dispersive power, as I showed you, it is given by the deviation of violet uh, ray and minus deviation of red ray divided by mean deviation. Okay, and then how do you calculate, and then you have this given here is the refractive index for violet and red rays. So how will you calculate the dispersive power from here? Anyone? Do you know any other formula that can be used here? You have mu, okay, and you want to find uh, the angle of deviation. So you have this formula, right? Mu minus 1 a, but you don't know a. The angle of prism is not given. But actually this is not needed, because let me show you. So del V will be so mu of violet minus 1 into A minus mu of red minus 1 into A divided by, so this delta mean will be mu mean refractive index, mean refractive index minus 1 into A. Now this A will be cancelled from above and below, right? Simply. So you don't need the information of angle of prism, and this minus 1 minus minus plus will get cancelled with minus 1. So effectively you have mu V minus mu R divided by mu mean minus 1. So this is also a formula for uh, angle of deviation, sorry, dispersive power in terms of refractive index. Okay, and you can calculate the mean refractive index uh, by simply just adding and by taking the average of refractive index for red and violet light, which will be 2.84 divided by 2, 1.42. Okay, so let's put everything here. Uh, so the dispersive power will be 1.44 minus 1.40 divided by 1.42. Oh, sorry, and minus 1. So this will be 0.42. Okay, and if you calculate it, it will be something around 0.05. Okay, it's also a simple problem. Is everyone fine with it? Are you guys have, is some noise going from my side? Actually, I'm in my lab, so you might hear some noise. People are discussing. So sorry for that. If everyone is okay with this problem, let me go to the next problem. Uh, so here we have a ray of light entering from rarer to denser medium. So this question is simple Snell's law problem, and the angle of incidence is given, okay, I. So this is a rarer medium, and this is a denser medium. Okay, and if the reflected and refracted rays are mutually perpendicular to each other, so this is the incident ray, and so some light will get reflected, okay, uh, R, and some light will be refracted. So will be closer to the norm, like this. So let me write it. So this one, let me write it. So this one should be R, and since reflected and reflected right, incident and reflected right angle are equal, so it is also I. And the question is, in the question it's given the reflected and reflected light rays are mutually perpendicular to each other. So this angle is 90 degree, and we have to find the critical angle. Okay, theta c. Uh, Now, how do you do that? So yeah, so obviously, I mean, we have to use the Snell's law. So theta c is given by sine inverse of 1 by mu, right? This formula we know, okay? And sorry for the disturbance. Okay, so yeah, let's focus here. So this formula we know. So we need to calculate uh, the refractive index of this material. And how can we do that? So only we have only this information that the angle between reflected and reflected light is 90 degree. So can anyone suggest how can we calculate it? Okay, so let me write more things here. So this angle will be 90 degree minus I, and then this angle will be 90 degree minus R, right? And so from the figure you can see that 90 degree minus I plus 90 degree minus R is equal to 90 degree, correct? These two angles I have add up, and which is 90 degree. So here you can get a relation between I and R, and they are equal to 90 degree. The sum of incident and refracted angle is 90 degree. Okay. Now, so you have R is equal to 90 degree minus I. And here in the options, you can see that the answer is written in terms of incident angle, right? So now we can use the Snell's law, which is mu equal to sine I by sine R. And you know the sine R, which is 90 minus I. So sine 90 minus I. So sine 90 minus I, what is it? Can anyone tell me? Cos, right? Cos I. So this will be tan I. So we have mu, and you can put here in this formula theta c equal to sine 1 by tan I. So 1 by tan I will be cot I. So the correct answer will be C, sine inverse cot I. Okay, this is also a simple problem. Anyone has any doubt here? It's just a simple calculation, right? We just derived the relation between I and R and used the Snell's law, and we had this formula for critical angle. So we calculate. Now the next problem, we have a ray of light is traveling from glass to air. So this is glass and this is air. So obviously, I mean, the light ray, uh, wait, I think the figure here is wrong, because it should not bend towards the normal. It should bend away from the normal, because air is rarer than the glass. So you can think of it like this. Uh, you can think it went wrong. So this is wrong figure. So light ray is traveling from glass to air. So this is glass medium, this is the air medium, okay? And this is the normal. So if the air if it will if it would have been uniform glass, the light ray would have been straight line, right? I mean, would have traveled a straight line. But since the interface, since the medium is changing and it's air which is rarer than the glass medium, it will bend away from the normal, something like this. And we want to calculate this angle of deviation, D. Okay. Uh, and its refractive index is given, mu of G is 1.414. Here we have mu 1. Okay, so this is also simple. We can just use the Snell's law. Uh, so mu G sine I equal to mu air sine R, and so uh, mu G is 1.414 into sine I equal to mu air is 1 sine R, and sine I. So in angle of incidence is 45 degrees. So sine 45 degrees is just 1 by root 2. So 1.414 by root 2 equal to sine R. You can calculate R. It will be 30 degree. So now you know this angle, right? and we have to find this angle, this angle. So what should you do? If you can if you know this angle, then you can calculate by subtracting from r. So this angle, because these are equal, these are opposite angles, this will be same as the incident angle. So D will be just R minus I, correct? Sorry, uh, no, not, sorry, I minus R. This is I, and this is R. Uh, Wait, something is wrong. What have I done wrong? Oh, hmm, it should be R minus I, right? But why R is less than I? Yeah, yeah. It is 1. Wait. Yes. Let me see. Oh, aha. Here I have done the mistake in this formula. Oh, no. This is correct, right? Mu G, because incidence is from the glass medium. Mu G sin I, mu air sin R, right? Then mu G is 1.414 sin I, 1 sin R, and sin 45 degrees 1 by root 2, correct? And yeah, under root 2 is just 1.414, right? So it will be cancelled, and sine r will be 1. Mhm. Okay, so then r, yeah, then it's r is 90 degree, and so the deviation is r minus I, which is equal to 45 degree, right? So that means this angle of incidence is a critical angle, because the after refraction it is going at 90 degree, right? Yeah, I think there is some problem with the, I mean, the question, then the problem is straightforward. If you have incident light at 45 degree, it is going like this, so the deviation is simply 45 degree, straightforward. I should have changed this angle. This 45 degrees should be something different. But okay, I mean, you understand how to go about solving it, right? So this is the main thing. Anyway, is it fine now? then let's go to the next problem. So here, yeah, this problem is little bit tricky. So the question is the maximum value of angle of a prism. So you have this prism. This is the angle of the prism. Okay. So what should be the maximum value of angle of prism? So A max. Is it equal to the critical angle? So critical angle is this angle of incidence after which this light ray goes to a 90 degree. The angle of reflection is 90 degree. That's what we call theta c. Okay. And then twice the critical angle, independent of critical angle, half the critical angle. So what do you think? Can anyone suggest any answer? Hello? Should it be independent? I mean, see, obviously, this when the prism is made, no one thinks about this critical angle. Okay, but then, as I showed, uh, this deviation that this prism will cause, it depends on the angle of the prism, and it also depends on the angle of incidence, right? I showed that plot, no? This kind of plot we had. So that means the angle of the prism and the incidence angle are both related somehow. Okay. If you change the angle of prism, the angle of incidence for which there will be a minimum deviation will also change. Okay. So that means this angle of prism and the incident angle are somehow related. Okay, so the simple way to derive it is okay. If in the derivation of this formula mu minus 1 a, uh, if you go through this the derivation of this formula, it should be in the lectures, or you can pick any ray optics book. You will find that, so suppose this is the beam of light coming, this is I, and then it's going like this is R1, here again it's going like this is R2. Okay, it will form a triangle like this, and this A is equal to R1 plus R2 always. Okay, this can be derived. This is a standard result. So you see, this angle of the prism is, it depends on the trajectory. Uh, it has something to do with the trajectory of the light. And now the R1 and R2, they depend on the angle of incidence or angle of emergence through Snell's law, correct? So to get maximum so to get the maximum angle of prism, we have to maximize these two also. And what is the maximum value of R1 and R2? R1 and R2 can go, so maximum will be what? 90 degree, right? And when this will happen, the angle of incidence will be what? Critical angle, correct? So then you have A equal to 2 theta C, because R1 will be also critical angle, R2 will be also critical angle. So the correct answer is twice the critical angle. Okay, so you have to just remember this result. Okay, this is standard result. Yeah, yeah, good afternoon. Yeah, no problem. Yeah, no problem. Mm-hmm. Mm-hmm. You're saying you're saying assign, no, this is for week 5. For assignment 4, I did the live session last Saturday. Okay, this is for the assignment 5. Okay, okay. Uh, okay. Then any doubt here? Is it fine? Okay, then if it's fine, then let's move to our last problem, the session. So here the question is, so this is a problem from last week topic from lenses. So the question is, a double convex lens of radius of curvature r is cut into parts, two equal parts by a vertical plane. So a double convex lens looks something like this, and we have cut it like this. So we have now two different lens. Okay, we have separated them, and if f is the focal length of double convex lens, so the original lens had focal length f. What will the focal length of these two? Okay, and since we have cut them equally in equal parts, they will have the same focal length, right? uh, Sorry. Okay, so how will you find the focal length here of these different lenses? Yeah, what 1 by f equal to Oh, how? Yeah, I mean, uh, sorry. So yeah, let's calculate it. Whatever you're saying. So this is just 2 by f, and then f equal to f by 2, right? This should be the answer. Oh, sorry. Then we can invert it and get 2f. Correct? So apparently the focal length of these two lenses will be twice of that of the original lens. I mean, it's little counterintuitive, but it's true. Uh, or I mean, this is this you can solve using the uh, to confirm it if it's so. This formula is derived from this lens maker formula, which is given as given by this mu minus 1 by r1 plus 1 by r2, right? From here you can get this formula, uh, but if you want to solve this using lens maker formula also, you can solve it, because uh, here you had r1 and r2 equal, uh, both equal. So let's put 1 by f equal to mu minus 1. This will be simply 2 by r, and for the plano convex lens here, uh, you have r1 equal to r, but r2 will be infinity. So 1 by r2 will be 0, right? And so you can calculate 1 by f as mu1 minus 2 divided by, it will be just 1 by r, right? And you can divide these two equations, so you will get f by f, so this will cancel, get cancelled, and you will get 2. So here also you can find f is equal to 2f, correct? The same thing, because this formula that you mentioned is derived from Lensmaker formula, so this way you can also calculate. Fine. Is anyone have having any question? This was the last problem, so we are almost done. Okay, thank you. My pleasure. Thank you. So yeah, I mean, yeah, yeah. So you can ask any general question if you have, also, and if not, you can leave. The session is, I mean, officially. So does anyone has anything to ask? Okay, if not, then thank you for joining. I'll see you again next Saturday. Uh, Bye. Thank you. Yeah, yeah. Tell me. 5. See, the yeah. You want me to start at 2:30, right? Actually, the problem is since yeah. So since this meeting time is not fixed by me, it's fixed by the NPTEL guys. So I don't think they will change the meeting time. But I mean, if you, so you have issue with this time 3 to 5, right? 4:15. Okay. Uh, See. Okay. Okay. Uh, yeah. Can anyone? Hello. I think there is an eco problem happening. Uh, yeah. Tell me. Hi. Uh, Today's 11th problem. Yeah. In this problem, 11th problem. In this problem, yeah, this one, right? Oh, this is week 5. Yeah, this is today. Today's. I mean, this session is week 5 session. You mean week 4? I mean the session before it. Oh, assignment of week 5. Okay, and so what is your concern? Let me. Let prism made of right angle triangle. Okay, one angle is 90 degree, right? Okay, then AB. So this is A, this is B, this is C. Which is the right angle? ABC or okay? C is 90 degree. Okay, let me can draw it again. Okay, let okay. Okay, thank you. So this is 90 degrees C. A is 60 and this will be 30, obviously. Okay, normally that means normal. Uh, okay, okay. So it is, oh, okay. AC and BC. Uh-huh. Okay. right. So suppose this is the normal. I understood the question. Let me try to solve it. So suppose this is the normal, okay? I have drawn the figure little wrong. So it goes inside and then totally internally reflected from here and here also. Can you mute yourself? Can you mute yourself? There is echo problem. Okay, thank you. So this is getting totally internally reflected on the both side, this AC and BC, right? And the question is, what is angle of sorry what is the question, the final question, what is asked? Please unmute yourself and let me know. Sahida, can you unmute and tell me is it asking refractive index? Sahida, are you there? Hello, are you speaking? I cannot hear you. Can you speak again? Hello. Okay, so can you write in the chat box what is the question? What is the final question? Saida, can you hear me? Oh, what is minimum refractive index? Okay, thank you. Okay, so minimum refractive index. Okay. So, uh, you know this formula of refractive index, which is A plus delta m by 2 by sine A by 2, correct? Now, since it is getting totally internally reflected at AC and BC, and I think it should be parallel, right? Uh, emerging from this AB, it will be parallel to the incident light. Is it so? Can you confirm? So as I mentioned, So this formula is only valid when incident angle and emergent angle are both equal, right? This formula. And so let me draw it again. So since this is 90 degree, okay, and so this is the normal here, and suppose this is the normal here. Uh, you can calculate. So this is 90 degree, and so this will be okay, I need a bigger page to complete this. Uh, okay, wait, the image is given in the question. Yeah, I need the exact image actually, because without that I cannot find the angles. So let me send you my email ID. Okay, can you please send me the problem there? 092. I am giving you my email ID. Please send the screenshot of the problem on this email ID. Okay. Yeah. Yeah. Thank you. So I'll provide the solution. Okay. Okay then. If you have noted down the email ID, yeah, you have noted down. Okay. Thank you. Then I'll close the session now. Okay. Thank you. Bye.